let me start with this. We all had to go through this process, so.
Not too worried about it.
All right, let me give you a minute to think about it. But the whole idea here is just to introduce yourself and some things on the questions. Let me just go to the next slide first. Homeworks, for example. I looked this morning. It appeared to me that everybody had no trouble getting in, signing up, registering. I looked at all the grades. Clearly, the first homework set wasn't all that complicated. Everybody did really, really well. But any problems with that? No? Okay. For some of you that want to know, I'm going to have the homework solutions posted in D2L by tomorrow. And what they'll do is I'll have a complete, they're really detailed. I'm a sort of step-by-step person, because I like to see exactly from one step to the next how you actually solve a problem. So you'll see it and go from there, and you can sort of take a look at that. That means you don't have to spend a lot of time in class, but if you see the way I did it and it makes no sense to you whatsoever, let's talk about that, okay? But let's have you take a look first, and then we'll see whether we can go forward with that one. It appears that everyone was able to create an account. Now, what we're going to do is Riley's going to sort of do a setup where she's going to look at the class roster and then compare that to the MEL roster to make sure everybody's in sync. But apparently, anybody have any trouble getting in? Yes? No on the MEL? You had trouble sort of registering?
Haven't yet.
Okay, so for those of you that either had trouble or haven't yet, right? Talk to your peers just to make sure if you have any difficulty, talk to them first, and then you can come and see me and we can talk about all that. By the way, it's also really okay. I know there were a few of you that emailed me questions about, hey, I didn't quite get this particular one. It's really okay for you to collaborate with all of your peers. There are a couple of reasons why. Because one of the things that's really interesting about the online homework set is that I've got it set up so that all the numerical parts of the problem are a little bit different for everybody. So the process to solve it will be exactly the same. But it allows you to sort of talk to each other, and yet you still have to figure out your own answer. So the calculations will be the same process, but the calculations using the numbers are a little bit different. So feel free to collaborate all you want. That would be great. And if you still are hung up, then you can give me a ring. As some people found out, I can try to answer the emails, but maybe not as quickly as you would like me to. And so it's a little bit tricky if you're under the gun on some sort of response. So start with your peers first. Also, feel free to post a question to the community page. Hey, I don't understand what Readey was talking about. Can somebody give me an idea of what this particular cost was he was discussing? No problem there either. So completely interactive. Okay, let me turn it now back over to Adam. Adam, why don't you go ahead and introduce yourself and tell us what's going on.
All right, my name's Adam Harkness. I'm a super senior in civil engineering. A recent accomplishment I'm proud of is I got a job offer this last fall after spending the last couple of years on active duty. Came back to school and I was kind of worried, finishing up my degree, I wouldn't get any job offers with no real, civil engineering experience. But I did, so pretty happy with that. And out of this course, just want to get more knowledge about the financial aspect of construction management, really.
That's great. Where were you stationed?
I was at Eglin Air Force Base in Florida for a while, and then down in Denver at Buckley Air Force Base.
Good, good. Well, I'm glad you're here safe and sound and ready to go. That's great. Very good. Okay, homeworks. So let me go ahead and just get started with today's topic of costs. And really, in order to get into the cost side, we've got to talk about cost terminology. And rather than sort of just give you lots and lots of definitions, here's a terminology sheet, if you will, that you can put in your notebook and hold on to it for a while. We'll go ahead and take a look at these over time, but we'll cover just a few of them today to give you an idea. So one of the reasons that it's important to look at costs and understand the kinds of costs that we have to worry about is because for the most part, that's what you're all going to have to deal with. So engineers, while they always are looking for the technical solution, we're going to combine the technical solution with the cost element of what does it cost to go implement that solution. And that could be a manufacturing cost, it could be a parts cost, it could be all kinds of costs. So understanding how costs impact the design and the manufacturing and the solution is really important as we go forward in your job. So let's talk a little bit about just getting some cost terms, sort of you understand what's going on. There's a term called consumer goods, which are really those products and services that are purchased by consumers. No big surprise, right? So things like food, clothing, toys, haircuts, iPhones, all kinds of things like that. There are the other kinds of goods known as producer goods, and those products are services that are the ones bought by businesses, things like aircraft engines, laser cutting machines, things like that. In some of the language that you'll hear by the economists in the country, you'll hear this term producer goods, consumer price index, for example, that relates to things like the inflation rate. And the inflation rate for consumer goods is a lot different than the inflation rate for producer goods, and so we'll talk about that in a couple of weeks if you're interested. For those of you that are taking notes, just again, all these things are now on D2L, so you can always download the notes directly and annotate them or go from there. There's this other term that comes out of the economics field called economic worth, which means goods and services have this thing called utility, which means if it didn't have any value to you, you probably wouldn't be buying it. So utility, value, how that kind of ties together. And value is often related to how much are you willing to pay for what you actually get. So that's kind of one way of looking at sort of this. So from an economics perspective, again, how many folks have taken econ, like either macro or micro? Some of you. So some of you that have taken this and already know this sort of stuff. So there's this terminology called perfect competition, which means lots of people are making the same kinds of products. So the price is as low as it can possibly be because everybody's competing with each other. And that's called perfect competition. Highly theoretical products or services, if you will, are provided by a large number of suppliers. So if that's the case, right, and generally what happens is there's not a lot of differentiation between all the products because you have so many people making them. They all kind of compete on the same sort of factors. And we would call that a commodity where you really can't tell the difference between one supplier and the next. So you go to the hardware store, you look for bolts and nuts. You don't even know who the supplier is because you can't tell the difference. They all make the same sort of thing. If you talk about wheat, for example, you don't know where the farm is that's coming from. Wheat from North Dakota might be very much the same as wheat coming from Colorado, if you will. So commodity kinds of things like that. And the important part here is that price quickly finds the equilibrium level down here someplace where everybody's competing at this price, and for the most part, the successful suppliers are able to make it at a cost somewhere down here so that everybody has kind of the same profit margin, if you will. And we'll talk a little bit about what all that means down the road a little bit. At the other end of the spectrum is something called a monopoly, where the entire market is controlled by roughly one company. So the theoretical situation, for the most part, products or services are provided by a single supplier. Now, there are a few examples of this where this really takes place, but one that certainly comes to mind is what happened 100 years ago or so, where J.D. Rockefeller formed the Standard Oil Company. And basically, remember the whole story about J.D. Rockefeller? You know, the whole idea of oil coming out of the ground in Pittsburgh someplace, or close to Pittsburgh. So Rockefeller was associated with all that. Started building oil companies, and then all of a sudden decided he was really successful. And then a lot of little oil companies started to pop up around the country, either refining operations or what have you. And all of a sudden he would say, well, I'm one of the bigger guys out there. So he would go to one of the smaller companies, maybe in Cleveland, if you will, and said, I'm going to make you a deal. Nick, I'm either going to offer you X dollars to buy your company, or I'm going to drop my price so far to the ground that you're going to basically go out of business. So those are your two options. What do you want to do? And Nick's going to probably say, okay, I'm going to sell to you. So now I own the Cleveland market. And then I'm going to go over to Maddie in California and do exactly the same thing and say, sell to me, or I'm going to put you out of business by dropping my price, because I can tolerate a low price for a little while, certainly long enough to put you out of business. And over a period of a few decades, all of a sudden, the Standard Oil Company pretty much dominated the landscape for all oil production and all refining operations throughout the entire United States. Now, what does that give Mr. Rockefeller the opportunity to do at that point?
Control the price.
Right. Price is whatever he wants to set it at which point it'll be the highest price that I can possibly charge where people are still going to be able to buy it. So that turned out to be not so much a good thing for people that were in the market for petroleum products. And the Supreme Court thought that was a pretty lousy idea as well. So right around 1911, it said, nope, that's it. You're too much of a monopoly. We're going to break up the Standard Oil Company into all these little companies that are all very regional. That will allow Maddie and Nick to kind of restart their companies now in California, Cleveland, and elsewhere, and compete a lot more competitively, if you will, with now the new regional Standard Oil companies that are out there. Well, that was the idea. And then all of a sudden, some of these sort of smaller regional companies started to reform. They merged to form bigger oil companies. And now today, you know, there are not that many players that are out there. ExxonMobil, Chevron, BP, a few others. What's it called then if there are only a handful of companies that are controlling the entire market? Anybody remember?
Oligarchy?
Oligopoly.
Oligopoly.
Yeah, oligarchy, that's one of the political side of things. So on the economic side, it's an oligopoly, where you've got just a few players controlling the entire industry. Not quite as bad as a monopoly, but still, they're not supposed to collude, if you will, in terms of talking to each other about what the market is supposed to do. But if there are only a handful of you, it makes life pretty good. There's another industry in the U.S., maybe even globally, that's also an oligopoly. Anybody have an idea? There are probably several of them, but it's one coming to mind.
Like Monsanto with like seed production?
Yeah, that's probably even more of a monopoly than anything else. And so what's going on with Monsanto right now?
Well, didn't they get just bought by some larger company?
They are in discussions for merging with Bayer, right, the Bayer company in Germany that's also kind of a pesticide fertilizer-based company, to try to now dominate the entire world in genetically modified seed production. So depending on where you are on that debate, that could be either a really great thing or something that's a little bit disconcerting. So there's that part of it. There's another industry that I'm thinking of. Casey?
Maybe the pharmaceutical.
That's the one I'm thinking about. How many pharmaceutical companies are out there? Right? A handful, I know, because I see them on advertisements at 5 o'clock every night telling me about all the diseases I'm certainly going to die from if I don't take their magic drug. So yeah, pharmaceutical industry is the same thing, all dominated by a few players out there. And again, is that a good thing or not? There's a lot of economic discussion behind it. But for our purposes, just to let you know, that's kind of the lay of the land right now. So let's talk about a few other costs. Now we're going to do some analysis based on all this. There's something called the direct costs. So these are the costs that if you're making something, these are the costs associated with the thing, the widget, if you will. The pieces, parts, the cost to actually assemble it or manufacture it, the cost maybe to ship it someplace into a distribution center. Those are all called direct costs. The indirect costs, not too surprisingly, are all the costs associated with everything else. So that would be, you've got the company over here that's making the widgets, and then you've got the stuff that supports the production of the widgets. So it could be like the IT part of the company, HR, maybe the legal firm. They're not involved in the actual day-to-day production, so their costs of part of the company are called indirect costs. Overhead, sometimes often synonymous with indirect costs, so I think everybody's probably heard of the term overhead. It just means everything that's not associated to the direct cost of things. And then the standard cost is something that we're actually going to figure out as well. Standard cost is, if I'm an engineer and I'm designing a pieces part, some kind of a thing, then the standard cost is, well, I just designed it to do this. It's made up of a bill of materials with these 5 parts. The part should cost $3.25 to make. So it's kind of like my theoretical cost based on my engineering analysis. And then what you can do is figure out, well, what does it actually cost when you go into manufacturing? But for the most part, the estimate of what it should cost based on the analysis is called the standard cost. Now, 2 costs that we're going to play with in just a second here. One is called the fixed costs. So in every company, there are costs that you have to pay regardless of whether you're making one product or a bazillion products. So things such as advertising costs, R&D, management salaries, has nothing to do with the actual volume of stuff that you're making, but you need to pay it in order to support the company going forward. The variable costs are all those things that have to do with actually making the thing. So materials, how many hours does it take for a technician to put it all together? That kind of stuff is associated with variable costs. So if I had to sort of say which one is which, and in general, if a cost increases or decreases with production volume, we can call it a variable cost. So if I had to say, what would this be? Raw materials, fixed or variable? Variable, right? The more I have to make, the more raw materials that I need. Direct labor, now direct labor, just by definition, would be the people that are on the assembly line actually making stuff. So direct labor, fixed or variable?
Variable.
Variable, okay. Here's an interesting twist to things. So if I were the heartless industrialist, right, I would hire and fire the direct labor people in line with what my production needs needed to be. So if all of a sudden production ramps up, I hire more people. So variable cost, for sure. If all of a sudden the demand for my product starts to decrease, I have to lay a bunch of people off, right? So my direct labor floats with the demand. So therefore, it's usually considered a variable cost. But let me ask you this question, right? There are some companies out there that feel that necessarily isn't the right way to run a company, because you have a tremendous impact on people's lives when you hire them and lay them off, depending on what your demand is going to be. So there are a few companies, not very big ones, mind you, but family-owned businesses that have a real relationship with their employees, that try to set the direct labor at a point that's kind of averaging over their overall demand cycle. Really important if there's like a seasonal business that they're involved in. That way, in the times where it's a little bit soft on demand, you know, they have other things. They do equipment maintenance or things like that. When demand is really high, then they might work a little more extra overtime or something like that. But for the most part, people are employed at a constant level, independent of what the huge demand shift is going to be. That's one way that there are some companies that were involved in the textile trades, I know, that developed a tremendous following by their employees because they know they were pretty safe. They didn't have to worry about whether they were going to be laid off the next time that the down cycle occurred. So that's one way of running your business. Under that situation, I would probably say the direct labor costs are more fixed. But that would be a more rare situation, I think, relative to what the economists and the accountants would probably think about. Rent, what about rent? Fixed, okay? You got to pay it whether you're making anything or not. Insurance, so there are a couple of kinds of insurance. There's medical insurance, there's also liability insurance, product insurance, building insurance, probably fixed, okay? Engineering salaries, here's also an interesting one. If you work for a big company, again, engineering salaries are often considered fixed because you've got the production department over here, which is largely variable, and you've got the engineering department over here, which sort of is independent of what's going on over here. So in that situation, they would be fixed. But I'd worked for a smaller company where the engineering team was pretty much driven specifically by projects that they would be involved in. So in that case, you know, if all of a sudden you're doing one project or two projects, maybe you would allocate your engineering cost to the variable category rather than the fixed category. So again, I think it depends kind of on the situation of what your company is actually doing. For the most part, though, people would say engineering salaries are probably a fixed cost because they don't add and lay off engineers depending on what production is going to be. Sales commission. So you have a sales team that gets paid part by salary, but mostly by a sales commission. Would that go up or down? So that would be a variable cost. Shipping costs, again, probably variable. Medical insurance, probably fixed. Machining fluid, variable. Utilities, gas and electric. This is a tricky one, too. Could go either way. Right? Could go either way. If I have a huge factory and all the corporate functions are in one end of the factory and all the production is in the other end of the factory, you can't really tell which half is using, you know, what's the corporate functions using in terms of utilities and what is the production using. So you can lump it all together and call it a fixed cost. If you've got your plant over here all by itself and it only does manufacturing, you might be able to say the utilities associated with that production could be variable. Now, why is any of this really important? Well, it's really important only in terms of where it ends up on the financial statements that we're going to talk about on Thursday. But one way you can actually tie some of these things together is something called the break-even analysis. Now, in every single business, one of the things that you're going to be able to calculate very early on is how many widgets do I need to sell before I break even, meaning the cost of developing the widgets and all that, making the widgets, equals all the other costs that I have in the business. So let's talk about the break-even analysis and what's going on. The way that the break-even analysis is calculated, which again is the number of units that you sell when the total revenues equal the total costs of producing them. So let's take a look at how this actually works out. Okay, so the total cost, let's start with that first. The total cost is the combination of the fixed costs that we just talked about, plus all the variable costs that we just talked about. So if I plotted cost on this axis by the number of units that we're selling on that axis, let's just say the fixed costs we said are a constant, right, because they're independent of the number of units. So that would just be a line that looks like that somewhere. And the fixed costs here would be things like management salaries and the building rent and stuff like that. Then what I want to do is look at the variable costs, and the variable costs are associated by the cost per unit. So if I'm making this cup, what's the cost to actually make this cup, times the number of cups that I'm actually producing. And so the variable cost has something that looks like this sort of slope with a or a line with a slope that's related to sort of the cost per unit times the number of units. Easy enough. Okay, so the total cost then is the fixed cost plus the variable costs. I add those two things together and I end up with something that looks like that. So that's my total cost curve, if you will. What about the revenue side, right? Total revenues, well, what's a revenue? Revenue is just the money you get from sales. So you sell something, sales and revenues are sort of the same sort of thing. The dollars generated from selling the products and the services. So you've got the total revenues is related to the price per unit times the number of units. Now, actually, that's not the slope, right? The slope of that is just the price per unit. But the total revenues is just the product of the price per unit times the number of units that you sell. If that's cost $3 for somebody to buy and I sell 100 of them, I get $300 of revenues. So all I need to do then to find the break-even point is to equate the total revenues with the total costs. That would give me the number of units that allows for that break-even, or where that crossover occurs. We'll just call that N star. And then I can calculate my way through all that. Why is that important? Because at the break-even point, which would be N star right here, anytime I sell more than the break-even number, obviously the total amount of revenue that I get exceeds the total amount of costs that I have. So I'm in a profit situation, which is always a good thing. And if all of a sudden the number of units that I sell is below the break-even point, now my total cost curve is higher than the total amount of revenues that I'm bringing in, so I'm in a loss mode. Not necessarily a good situation. Maybe that's okay temporarily if you're a startup or something like that, where you're just getting the number of units off the ground. But over time, you hope to be operating way, way out here some point so that you're in a very profitable situation going forward. If you are in a startup, one of the questions that an investor might ask you is, what's your break-even point before we start seeing a return on our investment? And you'll have to give them a number that says 10,000 units or 50,000 units or something like that, based on the analysis that you've come up with, which is just like this. Okay, well, there's a nice example in the book. So let's go through this example step by step and give you an idea of how to do one of these sorts of things. So example 2.5 is all about an engineering consulting firm, which doesn't actually make anything, but it's just the costs associated with the consulting business itself. So an engineering consulting firm measures its output in terms of billable hours, if you will, meaning how many hours am I able to charge the client in this kind of an operation. So here are the data inputs. The average personnel cost per hour right? Our C sub V number is $62 per hour. That's the cost to have Gabe, for example, work for the company on an hourly basis. May not be what he makes, but it's the cost of having him around, which is something else we'll talk about in the future. There's the client price. Well, what would Gabe's work charge the client? It would be somewhere in the range of $85 an hour. And if we said, you know what, we're a pretty big company, our annual fixed costs are on the range of $2 million per year, from those 3 data points, I can figure out how many hours do I need to charge out before I can start making some money. The other thing that we're going to find out is how many people I have times 40 or 50 or 60 hours a week of potential billable hours. I can come up with something called the capacity of the firm. Let's just say, based on all the employees we have and everybody's working 80-hour weeks, because if you ever talk to your friends working for McKinsey, they're all working 80-hour weeks, right? So you can calculate how many hours can you potentially bill out to clients under that scenario. In that case, how many hours are necessary for the firm to break even? Well, let's just step through it piece by piece and show you how this works. And then you can go back to the example in the book, and hopefully it will be very clear then what they're actually doing. So we said that at the break-even point, the number of hours that we would bill is sort of this N star. The total revenues equals the total costs. So all we do is we set everything equal like this. Total revenues are the price that we're charging to the customer times the number of billable hours that that customer is purchasing. That's one half of the equation. And the other half are the fixed costs, which we said is the building and management, and if I'm the boss, my $1 million salary, that kind of thing, right? But more importantly is the cost of having the employees around that are actually producing all these billable hours times the number of hours that they are charging out. So I can rearrange all that, right, very easily, and I say that my $2 million fixed cost divided by the difference between the billable price and the charge per hour, and I come up with a number of 85,000, 86,000 hours per year is the number that I need to charge. So if I'm a manager of this engineering consulting firm, for example, one of the things I'm paying really close attention to is how many billable hours are we charging out on an annual basis? Because if I'm less than 86,000, we're not making any money. Okay? So it's kind of a straightforward way to do this. Then you can take it to the next step, is if the maximum capacity of the firm is 86 or 160,000 hours per year, what's our utilization percentage at the break-even point? Well, I can just take my 86,000 hours per year, divide it by the sort of maximum capacity, and say I need to operate at 54% in order to sort of get into the black, if you will. So if we have, let's say, Gabe potentially working 80 hours a week, so long as he's billing 42, life is good, that sort of thing. Easy enough. Okay? Any questions about that? Let me just give you another twist. And this is my opinion on some of these things, so you can take my opinion for what it's worth. But the way that most people do this is we assume, and there are a lot of words here, so you can read them on the slide later, but let me just explain the idea here. More commonly, cost and revenue is treated as linear functions with respect to n, just like we've been talking about before. That makes life really simple when doing this break-even analysis. At some point, your company might have some really sophisticated cost and revenue models where n is actually part of a dependent factor on the cost model that you might be putting together. I'll give you an example of this in just a second. If that's the case, the algebra gets a lot more complicated, except for you guys, but the result is still the same. In order to calculate n star, you always just set total revenue equal to total cost, and don't worry about the math. The math will take care of itself. Let me give you a quick example of where this is coming from. So in problem number 53, in what's called the FE practice problems. Now, the FE practice problems are really interesting, the fundamental exam. Right? One of the things that I have to make sure that I do here is not just tell you what's really going to happen in your job, but also to give you enough information to pass the FE exam. So has anybody taken the FE at this point? Anybody planning on it maybe next year? Okay, several of you for sure. So I would say that sometimes in the field of engineering economy, we get into this sort of position where we develop some terminology all by ourselves, and we then put that into the FE test, so that we want to make sure that you understand all of that going forward. So here's why it's important to know this and then go forward. So let's just say number 53 in the homework, or in the practice problem section of the book, the company has determined that the price and monthly demand of one of its products is related by the equation. Already you can see it's getting complicated from a numeric standpoint. This isn't so bad. The fixed and variable costs, sort of on that basis, you can see that's easy. How do you calculate this? The way you would calculate it is you do exactly what we've done before. Total revenues equal total costs, except you've got to deal with this thing now and figure out how do you get that in terms of P. So you rearrange that whole thing and you get this interesting sort of quadratic form of everything. You end up with then a polynomial that looks fairly complicated. Then you just sort of solve through all that. That's not a terribly challenging problem for engineers. Okay? You're used to doing this all the time. My thing about this is this. This might make for a very interesting FE exam question, but I don't think you're ever going to see this in real life, because most of the time we don't really know costs so accurately that we can depart, there's a reason to depart from this linear assumption that we're making all along. So while it's important to know how to do it, stick with the fundamentals of total revenue equals total costs, and then you figure out what N star looks like, and let the math take care of itself. But in reality, I've never seen a situation where it's any more complicated than the real simple linear formulation that we just did in the example. Okay? But you may come across this, not in my homework sets, because I don't think this really occurs in reality, but you might see this on some other things related to, let's say, the exams that you might see. Okay, now it's time for you to practice some of this. So let's imagine that we're running a company. Okay, we're running Aqua Boulder, and Aqua Boulder dispenses a product called Only H2O via a vending machine that looks something like this. And Only H2O is just a water, right? It's sort of purified water, if you will. Not much to that. And we have you sitting around CU, if you will, and so we want to figure out how many gallons of water do we have to sell before we as a company break even. So if the average monthly fixed cost, monthly now, so that's an important number, fixed cost for the dispenser is $900. That would be this thing and then having somebody go around and maintain it and stuff like that. $900 per month. Each gallon costs 18 cents to purify, and that would include getting the water from someplace, purifying it, and then putting it in there. And then we sell it for 30 cents a gallon. So the first relatively straightforward question is, how many gallons per month do we need to sell to break even? So go ahead and take a minute to calculate that out. Tell me what you think. And it all comes down to the same simple equation. Total revenues equals total costs. And remember, the total cost is the sum of the fixed cost plus all the variable costs. So take a minute and let me know what you come up with. Yep.
7,500 gallons.
7,500 gallons. Everybody get 7,500 gallons? Is it Ryan?
Yeah.
Okay, how'd you get that?
I subtracted the 5 from the price you sell it at.
Okay, so the difference between these two numbers, which we just saw on the other example, for sure. Okay.
Which is how much money you're actually making, which is 12 cents per gallon.
Yeah.
Then I've divided 900 by 0.12 to find the amount of gallons that equals $900 at 12 cents a gallon.
Perfect. Everybody get 7,500 gallons per month? Okay. Easy. You thought that was complicated, right? So when everybody says we did a break-even analysis, now you know it took you less than 35 seconds to do this on a situation that who knows, not that complicated. But let's say then that, so scenario number 1 is 7,500 gallons per month is our break-even point. Okay? That's good. Now let's see what happens if we play around with some of our numbers a little bit to see what happens when things happen. So what happens if all of a sudden there's a 10% reduction in the fixed costs, which means maybe we figure out how to buy these dispensing units more effectively at a lower cost to us, for example. What happens to the break-even number of gallons per month in that situation?
Decreases.
Decreases to what? What's the new number?
6,750.
6,750. Okay. Everybody get that? So in situation number 2, we get a 10% reduction in FC, the fixed costs, and that leads to a new N star of 6,750 gallons per month. Everybody good? Okay. Now, let's take another scenario. What if there's a 10% reduction in the cost of actually purifying the water? So now we're looking at this number. Maybe because it's cheaper for me to buy, or I come up with a new technology that purifies the water more effectively at a lower cost. What happens in that scenario? So while you're thinking through that, I'll write the assumption on the board here. We have a number yet?
6522.
6,522 gallons a month? What do you think? Everybody else get that? All right. 6,522 gallons a month. So if you were the project manager on this, and part of your assignment was to obviously figure out how do you decrease the break-even point where you can start to make money, if you said, well, I can certainly reduce my fixed cost by a certain amount, right, in terms of the cost of the unit itself, management salaries, trying to slim down the number of people, or I could really look at how do I make things more efficient from a purification standpoint, which is more effective. I would say, this is a pretty good way to go. So what about the third situation? What if there's a 10% increase in the price? Maybe you find out I can't keep enough water in the system. Therefore, maybe my price is set too low. What happens if I increase my price by 10%? What do I get there? 6,000? Even? 6,000? Everybody get 6,000? Okay. 6,000 gallons per month. So again, raising the price, even just 10%, turns out to have a tremendous impact on the break-even point for our business. Now, of course, we've looked at each one of these things independently. We could sort of really, if we wanted to do this right, we would say, let's take a look at all three of these things and see what has the most influence over what's really going on. Under these scenarios, it's 10% in everything, so the percentage change is the same, even though absolute it's different. But the biggest impact is just raise the price a little bit, if you can. If you can't raise the price, then certainly taking a look at how do you make the process of purifying water way more efficient, or how do I figure out how to deliver this by these large units here more efficiently as well. And if you couple all those things together, you may find out you can drop your break-even point by maybe into the 5,000 number, which really will save your business a whole lot in terms of where it's going to be going in the future. So that didn't take much more than about 5 minutes to figure out how do you take a business and make it profitable by looking at the various factors that go on in how to drive this all forward. Let me shift gears now to another topic altogether for our remaining half hour or so, and that is design as it's related to cost optimization. So certainly there are a lot of things that one does in terms of engineers would look at the design of something and figure out how can I reduce the cost of all that. But there's an interesting approach that is easy to explain, talking about cost modeling, that I'd like to be able to point out. As most of you know, a big part of what your job is going to be is not only to design something of value, but also to figure out how can I design this at the lowest possible cost. And so you need to understand that relationship. Well, then the question is, what is the cost driven by? In many cases, you'll find as we go through an entire analysis, which you will very soon here, that you'll find that there's one thing in the cost that really drives everything else, whether it's materials, whether it's labor, whatever the situation might be. We call that the primary cost driver. So in any cost optimization study, we tend to focus on the one thing that's really the most important part. So we would really focus on how do you minimize the primary cost driver in a scenario like this. Well, let's just start talking about a few more costs that we would have to consider in our analysis. There might be the investment costs, which would be what are those costs of designing and prototyping the thing that we want to go build. Maybe we have to go buy some equipment to go put into our factory in order to build a lot of this. That's also part of the investment. Some of you may have heard of the term CapEx. That's a shorthand for the capital expenditures. Those are essentially the big expenditures that we've got to make to go buy the hardware, to go build all the stuff that we want to go do. And we'll talk a lot more about that in the future, too. Then there are these things called the operating and maintenance expenditures, otherwise known as the OpEx, okay, or the O&M costs. These are just the costs of keeping everything running. So if I bought this great big laser cutting machine, right, over time, I need to have somebody maintain it. Maybe I need to replace the laser component every once in a while. That's separate from the initial cost. So I got to worry about the cost of maintaining this laser cutter going over time. And then the other cost to think about is something called the disposal costs or other non-recurring, one-time only, or sometimes referred to as the OTO costs of generally shutting something down. So let's imagine then that my laser cutter is kind of done, right? It's lived its useful life. It's produced a whole lot of good stuff. I have to do something with it. I got to get rid of it. I can either sell it to somebody who maybe wants to strip it down for parts. Maybe I landfill it. But I just can't drive up to the Boulder County landfill site with a laser cutter in the back seat of the truck and say, here you go. It's going to cost me to get rid of it. I only have to pay that cost once, and it's done, which is why it's called a one-time only, non-recurring cost. But I usually have to take that into account in my analysis, as we'll see here in another couple of weeks, in order to capture the full cost of having some piece of equipment around. Okay, now a little bit of theory. Not too complicated. The whole idea is that we identify the primary cost driver, develop a cost model such that the total cost is some function of whatever that cost driver is, and then we minimize the total cost with respect to whatever that cost driver is. Okay, probably something that you sound familiar. There's another interesting example in the book, so you can follow along in the book. I just want to go through the example, but I want to put a few twists on it that, for me, make it a lot more meaningful. Example 2.6 in the book looks something like this. There's a little bit more to it, but let me show you the things I find interesting. So let's imagine the cost of flying a commercial aircraft is a combination of operating costs. Okay, let's not worry about the cost of the aircraft right now. Let's just keep things simple for this particular example. The cost of operating the aircraft, so it takes off, it's going to burn fuel and oil and stuff. I got to worry about that. And then there's this other cost that the airlines is concerned about, which is the cost of customers' time. Now, this would be sort of somewhat not so intuitive, but if you're in the airline services business and you can deliver customers more quickly to their destination, you're going to get more business from people, particularly maybe business travelers that are willing to pay a little bit of extra. So there's a value to the time that your customers have. The longer it takes, the more it costs you in the end. So let's just say that Superfast Airways has determined that the cost of operation, right, of taking this airplane and flying it off somewhere, is related to this function here, some constant factor, which the example will sort of calculate for you is this sort of just a constant with some funny units right there, times the number of miles that the plane travels, times its average velocity. Okay? and the average velocity raised to the 3 has power, because you would figure out that's where that all goes. And the customer time is not something that's so engineering oriented, probably what the marketing folks have come up with, but they said, you know what, the customer time, given the number of customers that we can fit on this plane, is related to $300,000 per hour times the time it takes to fly from point A to point B. Okay? So then the question is, how fast should the plane fly to minimize the overall cost for the company? Well, let's take a look at the pieces parts here and just go through one step at a time. We know the total cost to the company is the combination of the operating costs plus the cost of all the customer-related things going on as well. So I would just combine those two costs before, and so here's the cost of operation, here's the customer costs. That's really nice, except, well, the time factor, I got to relate that into units that make sense for me to go do. So if I take time and recognize that the velocity, v, is just distance over time, then I can substitute that in for the time. And then in our terms, then we could end up with this total cost equation with just a couple of variables that we can control and calculate our way through. The total cost is related to then the number of miles that we traveled times the velocity plus the $300,000 per hour times the number of miles divided by the velocity. Now that would be considered our quantitative cost model. So you can read this in the book, you can see it in the class notes. We don't need to go over this in great detail. For me, as I mentioned last time around, I love to create charts and graphs on this stuff. Okay? So what I did is I took this equation and said, let's assume that we're going to take a 1,000-mile trip. Right? That'd be like from here to Chicago, for example. So I set up a little spreadsheet where I've got the cost of operation, or the cost of passenger time, n, let's just say, is 1,000. That's the 1,000 miles. And then you can just set up and say, well, all right, what if I go 100 miles an hour all the way through 700 miles an hour, and I get my different costs, I sum up my total, and I can say, well, you can see here by going down the list that somewhere around 500 miles an hour, I get my minimum in my total cost curve. Okay? Everybody with me so far? Okay. Now, I also mentioned that for me, I'm not necessarily a tabular kind of person. I really like to see what things really graph out to be. So here's what it looks like when you graph it all out. Here's costs as a function of the velocity, miles per hour. Here's the operating cost. Turns out, just like driving your car, the faster you drive, the more fuel you burn, right? So you've got to worry about that. Here's the customer cost. The faster you fly, the faster you get the customer to the destination, so the costs go down. And you sum those together and you say, well, here's the curve that combines everything. And I can see that the minimum on the curve is right around 500 miles per hour. Makes perfect sense. But what happens if all of a sudden I don't go 1,000 miles, maybe I go 500 miles, which would be, I don't know, what's 500 miles from here? Here to Kansas City or something like that. Well, there's my cost of operation, doesn't look too different. Here's my customer cost, doesn't look too different. Here's the shape of the curve for the total costs. And you know what? It's almost exactly the same point as my 1,000-mile trip, which is really interesting. So in this particular case, the minimum cost in terms of how fast should I fly this plane is exactly the same, whether it's 500-mile trip or a 1,000-mile trip, almost independent. So that's kind of interesting. And then you thought, well, why would that necessarily be? I had this sort of the number of miles in the master primary cost driver cost model. What's going on? Then we can do what the engineers understand how to do. Take a look at this analytically and see what's going on. So you know that if your total cost model looks like sort of the sum of the two costs here, how do you find out the minimum in any type of cost model? Right? You take the derivative with respect to the parameter that you're really interested in. You set that all equal to 0, and then you solve for it. So if we take the derivative of c total with respect to the velocity, we set that equal to 0. That's the expression for that. And guess what? Right? You've got the velocity to the 1/2 power here. You've got the velocity squared, but it's in the denominator here. The velocities, or the number of terms, actually all cancel out in terms of the miles of travel that you've got. So the velocity term ends up to be completely independent of the number of miles that you travel, which gives us the same answer regardless of what we wanted to do. So in this case, we can now calculate specifically that the optimum speed of the plane over the entire trip should be 490 miles per hour. Okay? So in a lot of the examples that you're going to see, figuring out how do I model the costs is the way to sort of get at this minimization. Now this turns out to be a really nice example. Maybe the reality is not so easy to go do all this, but the techniques are exactly the same. You create some quantitative model of cost relative to something that you're interested in, and then figure out how to minimize that relative to one of the variables or maybe even two of the variables. That was what we call a continuous cost optimization problem, where the speed of the plane can go from 0 to whatever we want it to be, and I can calculate this from a very nice continuous set of assumptions going on in the process. That rarely happens because we rarely understand the cost model quite so specifically as what maybe we just saw. So the more common situation is known as a discrete cost optimization scenario, where the minimum in cost is sort of either A, B, or C, depending on the scenarios that we might be talking about. So if you have 3 different options of a product, for example, then you get to calculate which option might be the best. So let's take a look at this example here, and then we'll start to wrap up for the day. Acme Chemical is evaluating 2 different electric motors to drive a mixer and needs to perform an economic study to determine what to purchase. This is a classic engineering example for things that you'll be seeing in the future. The motor will produce 75 horsepower. Now, this is really important. It'll produce 75 horsepower. It'll be operated 8 hours a day, 365 days a year for 1 year. Maintenance will be performed in the second shift, so we're assuming there's no downtime in the operation of the motor. Okay? At the end of its life, it'll be done. So we don't have to worry about that sort of disposal cost at this point in time. We will later for sure, but not yet. So let's assume Acme's electric power costs 16 cents a kilowatt hour, which is high, maybe what you might see in California. Then your question then is, which motor can I buy if I have 2 options? If I have motor A, where I buy motor A for a price of $3,200, or I spend a lot more money on motor B. What's the difference? Well, the annual maintenance cost of motor A is less, whereas the maintenance cost for motor B is a whole lot more at $450. But the efficiencies of the 2 motors are really different. So the efficiency of the motor A, the cheaper one, is only 75%, and the efficiency of motor B is more like 85%. So you pay for the efficiency. It may cost a little more in maintenance, but you pay for all this. So the question then is, which motor is the most economical to own and operate for the year that we're interested in? So how do I calculate this? There are several components that I need to worry about. How do I calculate which motor should I buy? Do I just worry about the initial cost, the price? Probably not, although that's included in maybe the analysis. What else do I need to worry about? Jeff?
The operating cost.
Which would be composed of what? What's it consuming while it's running?
Electricity.
Electricity.
The price of electricity.
Exactly. So the price of electricity, I got to worry about that, times how much power it's actually taking to run. Okay. So the price of electricity, how many kilowatt hours am I going to consume over that 1 year period? What's the other piece of the operating expense that I have to worry about? The OPEX. The maintenance cost. So I've got the CAPEX, right? The cost to buy the motor, and the OPEX, which is a combination of the maintenance costs plus the cost of electricity to run all this. So let's figure this out. Everybody have these numbers down? Because we're going to calculate this and see how it all goes. Right? So everybody have the numbers? Okay. Let's just look at then a few of these sorts of things. If the total annual cost is the initial cost, which we said is the CAPEX, plus all the operating costs, or the OPEX, the total annual cost is related to the purchase price, plus the cost of electricity, which we said is a function of the power that the motor has to produce, also ties in the efficiency of the motor itself, the rate that we pay for the electricity, which we said was 16 cents a kilowatt hour, and the time that this thing is going to run. So let's assume that when we turn the motor on, it immediately gets up to speed, and so it's producing 75 horsepower output at whatever I need to do. And then I've got the maintenance cost, which we said was also a constant. So if I just wanted to calculate a few things here, I would say cost of electricity is related to the power, then related to the efficiency. So if it produces, let's say, 75 horsepower as an output, the input, which means how much power the motor actually consumes, is related to how efficient it is. If it were 100% efficient, what would the incoming input need to be to produce 100 or 75 horsepower output? 75 horsepower. If it were 50% efficient, how much input power does it need to produce 75 horsepower output? 150. Okay, so you get the idea? So obviously the efficiency factor enters into all this. So go ahead and plug these numbers in to calculate what's the total annual cost of owning and operating, the O&O costs, if you will, for these two motors. And then let's take a look at how we calculate that and go from there. So go ahead and plug some numbers in and tell me what you come up with.
Conversion factor.
For what?
In kilowatt hours.
Oh, yes, let me go back. 1 horsepower is 0.746 kilowatts. That's a really interesting point. Is it Connor? Okay. Now, one of the things I have to say I've discovered in not just doing these things in class, but I spend great deals of time on the job, is converting units from one thing to the next. What's really interesting about working in industry, depending on the kind of industry that you're in, it will be all SI units with metric system, making life somewhat simple, or it could be all English units with foot-pounds and things like that. And you have to figure out how to go back and forth really easily. I must have 3 books plus a couple of apps on my phone that do nothing but all this sort of conversion, unit conversion stuff. So I'm sure you're all good at it, but for me, I don't keep any of this in my head, so I just do to go ahead and make it this way. Okay, let me go back to this and then let you figure it out. So I mentioned at the beginning of class that I got my FCQ scores from last semester, and one of the comments that I got was less talking, well, they didn't quite say it that way, but more in-class sort of problems like this. So we're going to try to do a few more of these than I've done in the past, just to give you some experience in running with it. Ryan?
Back to the numbers.
Yes. No problem. I'll go back and forth all day long, so. How are we doing? So far, so good? Sorta? I bet if I asked you, design a motor that achieves 85% horsepower, you could probably do that off the back of an envelope. right? So that's what makes these problems really fun and interesting, is now we get to think about the economics of it all. No rush here. We've got plenty of time. I just want to make sure everybody's comfortable with it, and then we get some consensus on some answers, and we'll go ahead and step through the pieces parts. All right, we'll go one more minute, and then we'll see how we ended up here. Okay, let's see how we can come together on this one. So let's imagine you just started in your job, okay? And the challenge is your company needs to buy a motor, maybe for the manufacturing facility, or it's part of the product that you're doing. And I'm the sort of engineering manager, and I go to Adam, and I say, Adam, I'm off to a meeting. I got to know, which motor do we get, A or B? B. Okay. Okay, I'm off to a meeting. I got to know, which do I buy, A or B? Why? It's more efficient, and that leads to?
Saving more money.
Saving more money. Did everybody come up with an A or B answer? Did we all come up with, for the most part, B? So let's take a look at each step of the calculation and see where we end up here. Let's first just talk about the cost of electricity to operate the motor. Remember, we said that the sort of efficiency and the output are inversely related. So my 75 horsepower motor operating at 75% efficiency actually requires, I don't know, what's that translate into? 100 horsepower plus of input power to get this thing running. I can then do my conversion of kilowatts to horsepower, that sort of thing. I can then multiply that by my 16 cents per kilowatt hour, which is the rate of electricity that I'm going to have to pay. That's 8 hours a day times 365 days a year. Just the electricity cost to run this motor is $35,000 a year. It's a lot. So if I take the annual cost of motor A, I look at the initial price of $3,200. I add my $35,000 power consumption cost, add my measly little $250 worth of maintenance cost, and my total cost of operating this is $38,303. Did those of you that were able to get through the whole calculation come up with something close to that? Yeah. Okay, let's do the same thing for B, motor B. Cost of electricity, let's start with that. 75 horsepower divided by its higher efficiency rating, times the conversion factor, times the rate of electricity, times the time that we're going to operate, it's still high. It's still $30,000 plus per year just in the electricity to run the motor, which maybe if you've seen, how big is a 75 horsepower motor? Right? It's probably pretty big. It's not something that you would put on your desk for sure. You add then the higher cost of $5,900 and the measly little $450 maintenance cost, and then I end up with a $37,000 sort of annual cost. Everybody come up with that number? So clearly, when I compare these two things together, which motor is the most economical? The higher efficiency, even though it's more expensive, it's cheaper over the 1 year that I operate this to get the more expensive motor because of its higher overall efficiency, even though initial price is higher and the maintenance costs are higher. Because in this particular problem, the primary cost driver is not the price or the maintenance, it's the power consumption associated with producing 75 horsepower. So the greater efficiency of motor B more than outweighs its higher initial price and the higher maintenance costs. Not something that if you were to walk into your what's called the purchasing office necessarily, right? Everybody know what the purchasing office does or the procurement office? They're the folks in a bigger company that actually do all the buying. Okay? You would say, here are the 2 motors that we want to buy, and we're going to buy the more expensive one because it's cheaper to run over time. The purchasing person, who is generally compensated on minimizing the first cost of a lot of the stuff, is going to want you to justify why is he or she putting their job on the line to buy the higher cost motor, even though you can demonstrate now that you've got the greater efficiency and that leads to the lower overall costs. So, not necessarily intuitive, but you've got to be prepared to answer the kind of tough questions when you actually go through some of these exercises. Well, for the environmental part of the equation, what's the impact of efficiency on carbon footprint? Okay. Obviously, I'm consuming less power, therefore I'm requiring less power in the first place. So if I had to calculate the carbon footprint of the motors based on maybe how much CO2 or something like that each motor would have, I could put a number of that based on just power consumption and go forward, see what happens there. Then the question is, okay, if you're living in a place like California where electricity costs are really high, then the analysis that we've done is really pretty good. What happens if you live in some place where the power costs are really low? Last time we did the biogas example, it turns out Atlanta is really close to some major power producing facilities. The cost of power in Atlanta is only like 5 or 6 cents a kilowatt hour, really cheap. You plug that in, it may give you a different answer, because if the cost driver is power consumption and the cost just went down a whole lot, maybe all of a sudden now the first cost becomes more important. You don't know. In fact, you could probably calculate what does the cost per kilowatt hour need to be where all of a sudden that sort of transitions. But for the example that we have, certainly motor B is the better choice overall. That also goes to this whole question of energy efficiency. And I know as engineers you hear a lot about this in probably all of your courses. Certainly the environmental engineers talk a lot about the efficiency of anything, right? Because clearly the less electricity that you're consuming, the less electricity is required to actually buy in the first place. So that's always a good thing. Less electricity that you're generating means fewer emissions. And not only are we talking about greenhouse gases like CO2, but if it's coming out of the Comanche power plant or the coal-fired power plant in downtown Denver, then you also need to really think about life cycle costs of things like the SO2 emissions, nitrogen oxide emissions, maybe other soot emissions as well. So the whole idea then is if you need less electricity to run sort of more efficient types of equipment, then maybe you can even think about something really clever, which is if I only need so many kilowatts, maybe I can generate all that on site, which, if you recall, was one of the decisions that the wastewater treatment plant needed to make last week, was if I generate electricity from the biogas, is that sufficient to run the plant? If the plant is really running efficiently with LED lighting and very good insulation for heating and cooling, that might be a really good thing. So higher efficiency drives all kinds of lower costs throughout the system, as well as all the environmental benefits that you get from all that. Okay, one more thing. So we've looked at this scenario where we're trying to minimize cost, right, by looking at the cost driver, you can do exactly the same thing if your goal is to maximize the profit. Now you don't worry so much about what are the cost pieces, but what are necessarily the cost and the revenues that I get, and how do I optimize where those things happen over time. So you can go through the exact same analysis using a profitability motive, if you will, and all you do that is you derive the total revenue and total cost equations that we've done before, probably in some function of the number that we sell. Set the profit as the difference between the total revenue and the total cost, and then you maximize the profit with respect to the number of units that you're trying to sell or whatever other factor you might be interested in. And you can do that analytically, you can do it graphically, whatever. Doesn't really make any difference, but the process is exactly the same. That's it for today. So let's talk a little bit about what's going to come next, right? Chapter 2, we're going to talk about costs a lot more, so take a look at 2 if you haven't seen it yet. We're going to look at cost estimation starting pretty soon. We're also going to talk about financial statements on Thursday, which will be really fun. Everybody know what a P&L is? Profit and loss statement, otherwise known as the income statement or the statement of operations or all kinds of things. We're actually going to do an exercise where we build a profit and loss statement based on some thoughts that all of you have on certain things. There's some new homeworks. Again, not a whole lot different than what we just did as examples in class today. They're all up in MEL right now. Doesn't look like anybody had any trouble with that. For those of you that haven't figured out MEL yet, give it a try, talk to your peers, and go from there. I do think Riley sent out an email with a Google Doc for everybody to sign up for the lead posters. Okay, make sure that you sign up as a lead posting person for the participation grade at some point throughout the semester, and we're going to start that all on next Tuesday. Any questions? All good? If you have any questions or comments or hang-ups on some things, come and see me. Otherwise, we'll see everybody on Thursday. Thursday will be an interesting day, a little bit different than today, I can assure you. Yes.
The reason I couldn't get an MEL is because I was trying to get the book, not in the bookstore.
It isn't? Oh,
no.
Yeah,
Like price it out.
Right.
And I was wondering if like the subscription comes with the book and I have to buy it new or something.
No, you can buy the ebook version if you want.
Okay.
And the ebook version, unfortunately, it's one of these things like everything else. It's kind of like renting it. You pay the $120. You get the e version of it, and then it gives you access to